So elastic potential energy is the energy, it could be in any body that can undergo a deformation, and the energy that is stored due to change in the shape of the object due to deformation is called as elastic potential energy. So let's have a look at the calculation, and I'm going to draw a very simple graph over here. For example, we have this thing, and I'm going to label the axis. Let's say this one is force in Newton, and this one is extension in meters. Extension can be represented by E, it can also be represented by X. Both the notations are acceptable. Now let us have a look at the derivation. So there are different ways you can derive the expression for the elastic potential energy. Now one of them is that you can consider the area of this shape, the shaded area, that is the area between the force and the extension axis. So we have to shade the area that is towards the extension axis, and area in this case would be 1/2 times base into height, because this is a triangle, and the next step would be area equals to 1/2. Base is extension, height is force, so it would be the product of these two. So 1/2 Fe. This is the expression for elastic potential energy. The other method is that you write down this thing, work done on the spring equals gain in elastic potential energy. So the thing is, where does the elastic potential energy in the spring come from? This comes from the work that has been done on the spring while you extend the spring. So you know the formula of work done. The work done in that case should equal to the elastic potential energy. But what does the work done equal to? Mathematically, work done is force times the distance covered in the direction of force. And if you see, this thing is very important. You can use this formula only if the force is constant. But if you take a look at the graph, the force is not constant in this case. The force starts from 0 and it increases, let's say for example, all the way to 4 Newton. So I'm going to explain it through the graph, and we'll label the axis first. This is what we do before anything. Force on y-axis and extension on x-axis. Okay, so let's say this is the situation that we have where proportionality has been reached. At a certain value of force, there was a certain extension. So at a force of 2 Newton, the extension was, let's say, 2 meters. And if you want to make it more realistic, you can label the extension in millimeters, because 2 meters would be very dramatic extension. It doesn't extend that much, the springs, and that's why in most of the examples the extension would be given in millimeters or centimeters. लेकिन जो पहले आपने force लगाई है, that is F1, we call that force as F1, and in response to that force, the extension that is produced is, the produced extension is E1, and you increase the force. So this one was the force F1, and then you increase the force to F2. ठीक है, so I was just working on the graph, और इस पे मैंने शो किया कि the initial force was F1 and the extension was E1. ठीक है, यहाँ से यहाँ तक जो extension है आपकी E1 है. And secondly, the second force was increased to F2, thereby causing the extension E2. Now the shaded area between these two would be representing additional strain energy, and the formula for this one would be, if you want to find this one through the graph, you can find the area of the trapezium, which is a plus b divided by 2 times height. Height means the distance between the parallel sides. And if you want to write down the expression, it could be written as 1/2 F2 E2 minus 1/2 F1 E1. One of the expression is this. And if you want to write in terms of the spring constant, then you can write it like this: 1/2 K E2 square minus 1/2, okay, 39.24 into, and the extension is at that point is 20 millimeters, which is 0.02 meters, minus the second force, or the first force was, ठीक है, पहले आपने बड़ी वाली force ली, keep it in mind, पहले बड़ी वाली extension or force and then the smaller one, otherwise your answer would be in the negative sign. So 2 kilograms would be converted to, हो जाएगा आपका